In the last lecture video, we talked about the activating, deactivating ortho, para, and meta directors. And we're going to talk a little bit more about that as in terms of reviewing and then finishing up the reactions of the alkyl or of benzenes. So just remember that we had a list of activating and deactivating groups. The activating groups were things like with an N attached, with an oxygen attached. And notice that in this more detailed list, we do have a nitrogen. When a nitrogen is attached to the ring or when an oxygen is attached to the ring, that is an activating group. Now, also notice that when the nitrogen of an amide is attached to the ring, that the ring would then be activated. When the ring is attached on the other side to the carbonyl group, it would be deactivated. So we have to be careful when we have amides or when we have esters that we make sure that we look at the atom that's attached to the ring, whether it's an oxygen where it would be activated versus a carbonyl where it would be deactivated. Then alkyl groups and benzene rings were also activating. And then the deactivating group started with halogens, all the carbonyls, including the SO3H group, which looks like the X double bond Y group, which is why it's classified here. It does the same thing. And then NO2s and ammonium. And then these CF3 and CCl3 are deactivating because when you attach a CF3 group to the ring, the fluorines all become delta minus, leaving the carbon very strongly delta positive, which then is going to pull electron density out of the ring and deactivate it. Ortho-para directors are the activating groups plus the exception, which is that halides are deactivating, but they are also then ortho-para directors, and then all of the deactivating groups are meta-directing. And so we'll talk a little bit more about those reactions. So this is a much more detailed list than you need to know. Here is the list that we talked about in terms of listing them now from top to bottom. So we have the nitrogen-oxygen ring alkyl group. Then benzene is kind of our standard. It's our baseline. And then halogens, all the carbonyls. And we don't differentiate between carbonyls. And then finally, nitrile, C triple bond N, NO2. And then finally, the N plus. So these are ranked number 1 to number 10. And you need to know this list. You need to know which ones, how they are ranked, because in order to do problems of dye-substituted rings, which we can do now, we are basically, as we said in the last lecture video, we're going to look at the groups that are attached to the ring. The group that is the highest on this listing will then do the direction. So for instance, if I was to say what is the major product of this benzene plus bromine and FeBr3, the first thing we do is we determine what is the electrophile here. And the electrophile here would be Br+. So where is the Br+ going to add to the ring? Well, we look at the carboxylic acid, which is a carbonyl, versus NH2. NH2 is the higher on this list. So it is the most activating in this case, but it certainly is higher than a carbonyl group. And so we would say it's going to do the direction. So this is going to direct. What kind of director is it? It's an activating ortho-para director, so it's going to direct the bromine to go there and there. And anywhere there is a substituent, we can't put a group. So this ortho position over here is blocked. And so we would end up then with 2 different products. We would end up with the bromine adding ortho to the NH2 group and we would end up adding the bromine para to the NH2 group. So these would be our major products of the reaction. Now, if you're concerned about the sterics here, we're not going to invoke sterics in these kinds of reactions, but there may be a point where we would say that because the bromine is a fairly large atom, having it add next to the NH2 is not going to be as favorable as adding it para. But right now, we're just going to, if I asked you to write these products, you would write both of those products. So here's another example of this methoxychlorobenzene, para-methoxychlorobenzene. And so with nitric acid, sulfuric acid, what is our electrophile? It's NO2 plus. Of chlorine and methoxy, which one is the higher on the chart? It's methoxy. The methoxy is an activated group and much higher than the halogen. So that means it will direct, and it will, what kind of director is it? It's an ortho-para director. So it would direct ortho to itself. And there are two ortho positions, but realize that there's only one product that would be formed in this reaction, because when the NO2 group adds ortho, it would not matter whether it added to either of those two positions. We would just get this one product. So when you're doing these reactions, you just write the unique products, which in this case would be this one. If they have the same name or if they have the same structure, then you would not write both of those because they would be the same product. Or if you wanted to write them both, just indicate that they are the same product. Okay, again, this cannot add para because there's already a group there. Looking at this bromonitrobenzene, this this meta nitrobenzene with CH3Cl and AlCl3, what does that produce? That's Friedel-Crafts alkylation. So it's going to produce a CH3 plus. And where is that electrophile going to add? Well, if we look at bromine versus nitro, which one of those is higher on the chart? Well, they're both deactivating, but bromine is higher than the nitro group, so therefore the bromine is going to do the direction. What kind of director is it? It is an ortho-para director, so it's going to direct ortho to itself and also para. Now, there is a steric hindrance issue. We never add groups in between the meta disubstituted or 1,3 disubstituted. There's not enough steric space here for the CH3 plus to add into that carbon, so we do not add in between groups. So therefore we would just get two products of this reaction. The CH3 would add in this position, would be product 1, and then the other major product of this reaction would be to add the methyl group para to the bromine. So these would be our two products of this reaction, but we'd never add in between the 1,3 or the meta disubstituted groups. The steric hindrance does not allow that. Okay, so we can do reactions. We could continue on if we had another, if we wanted to react either of these with another electrophile, we would just look, and now the methyl group would be the highest on the chart, and so it would do the direction, with again the same proviso that you can't add in between 1,3 or meta disubstituted groups. So that's pretty straightforward. Determine the electrophile and then add it to the ring after finding out which group on the ring is the highest director, the highest ranked director on this list. And again, I will say that the group on the ring is doing the direction. The group that's the electrophile is being told where to go by the group on the ring. Okay. So now what I'd like to do is kind of turn the tables a little bit and talk about, well, how do you plan a synthesis starting from benzene? How would I make this molecule? And there's a couple of aspects to this that we need to know about. First of all, if I'm going to make this, and this is going to be an ethyl nitrobenzene, and it's meta-disubstituted, the first thing I need to know is what reagents do I use to add the nitro group? What reagents do I use to add the ethyl group? And so that should be straightforward, and this is where you're going to have to know your reagents as well as knowing how to write the products of the reaction. So we would add a nitro group by adding HNO3 and H2SO4, and also adding, then the ethyl group would be ethyl chloride and aluminum trichloride, although you could also use FeCl3 as well. So that's the first step, is how do we add those groups to the ring? Then secondly, what about the order in adding those groups? Because it's not just enough to know what reagents, we need to know the order in order to make these meta-disubstituted. So which group should I add first here? Should I add the nitro group? Should I add the ethyl group? Does it matter? Do you have any sense of which one you should add? The video is going to stop here, and I'm going to go ahead and ask you that question so you can go ahead and choose. Which group should I add first? Nitro, ethyl, it doesn't matter, or I have no idea. Remember, this is participation, so the last one, none of these are going to hurt you, but I'm just curious as to what the order you think it should be, or if it even matters. Okay, the order does matter. And I need to add these two groups meta, which means that in order to get these groups meta, I need to put the meta director on the ring first. So of these two, which one is the meta director? It's the nitro, because it's deactivating. So what I would say in this case is I need to put on the nitro group first. And when I do these problems, I like to put the groups on in the same positions as they're in the product, so that way it makes a little more sense. And then when I add my ethyl group then is going to be directed by the nitro group to add meta. So then I would say, well, okay, I'm going to use nitric and sulfuric acid first to put the nitro group on the ring. Then I'm going to add the ethyl chloride and the aluminum trichloride to then add the ethyl group, and the nitro group then would direct that CH3, CH2 plus the electrophile to the meta position. If I reverse this, what would I get? If I put the alkyl group on first, it's an ortho para director, and so I would get the ortho and the para product. So the order does matter. And so we have to be aware of what group do we add when we're sort of planning out our synthesis. And this is just a 3-step synthesis to begin with. So that's what we have to pay attention to. Now there's also going to be times like this reaction where we look and say, okay, I need to put a carboxylic acid group and I need to put a SO3H group on the ring. Well, I know how to put the SO3H group on the ring. It's going to be sulfur trioxide and sulfuric acid. That's what puts the SO3H on the ring. But how do I put a carboxylic acid group on the ring? Let me tell you right now how you do not add the carboxylic acid, because people will do this and I will mark it off. People will think that, oh, well, can't I just do this with aluminum trichloride? No, you cannot do that. Why? Because this compound right here is unstable. And in the next lecture video, we will also see that this compound is unstable as well. that is also unstable, and so you cannot use this set of reagents to add an aldehyde to the ring. Okay, so you cannot use Friedel-Crafts acylation to add a carboxylic acid. All right, if you do it, you won't get any points. So in terms of how do we put a carboxylic acid group on the ring? Well, this is where we should probably think about some of the reactions that we've talked about before. So one way I could think about doing this would be to put an alkyl group, any R group, any alkyl group on the ring. What reagent did I use to convert that ring, that methyl group, that alkyl group into a carboxylic acid? And this is obviously the limitation on the lecture video, unless I wanted to add this question into the quiz. But unfortunately, when the video stops, I have to give you multiple choice answers. But let's just, what is it? Well, remember, it's CaMNO4. If I oxidize a side chain, it becomes a carboxylic acid. So that's one way to put a carboxylic acid group on the ring. The second way is, could I take a bromobenzene and then react it with magnesium metal to form the Grignard? I can do that. And then what do I react that Grignard with, followed by a then H plus step, in order to make the carboxylic acid? And you would have to go back and look through your notes, but it would be CO2. So another way to put a carboxylic acid group on the ring is by putting a bromine on the ring, making it a Grignard, reacting it with CO2, and then you have the H plus H2O step. How did I get the benzene ring, the bromine on the benzene ring? I used Br2 and FeBr3 or AlBr3, which of course begs up here, how did I get the alkyl group on the ring? Well, I just took and reacted that with something like methyl chloride and aluminum trichloride. And that put any, you can put any alkyl group on the ring, because when you oxidize it, it's going to form a carboxylic acid. So there are groups that we do know how to add to the ring. It's just going to take multiple steps. And so in this case, as I'm looking at this reaction, I have multiple ways to put the carboxylic acid group and the SO3H group on the ring. So in terms of the order, which group should go on first? Well, I could use this SO3H group. I could put that on. So I could say, well, okay, let's, first of all, let's get a new slide here, because that would be helpful. And let's take our benzene ring and let's put the SO3H group on the ring, because I know the SO3H group is a deactivating meta director from that more comprehensive chart that I used before. And also it fits the X double bond Y group. So I can put the SO3H group on the ring like this, and I know that's going to be a meta director. So then I could say, well, let's go ahead and just put generically any alkyl halide and aluminum trichloride or iron trichloride, and let me put my R group, because my SO3H group is going to direct that into the meta position. And then finally I could use KMNO4 and oxidize the carboxylic acid, oxidize the alkyl group to a carboxylic acid. So let me pull that down and then convert that alkyl group into the carboxylic acid. So that's one synthesis. One of the things I will point out though is that what if I didn't want to make this group, what if I didn't want to make this meta, but what if I wanted to make this para? And not with the R group. What if I wanted to make this para with the carboxylic acid? What if I wanted to make this molecule? I know how to put the carboxylic acid group on the ring. I know how to put the SO3H group. But what's my problem here? My problem is they're para. And so in this case, if I wanted to do this, if I wanted to make this molecule, what would I do? Well, I would have to think about this as saying, okay, let's put the alkyl group on the ring first, since I know it's a para-director. And so I'd put my R group on the ring first. Now I'm not going to oxidize it yet because I need to put the SO3H group para to it. So then I would say, well, now let's react with SO3H and H2SO4, the fuming sulfuric acid, and now the R group is going to direct that sulfonic acid group to the para position. And at this point, there's a lot of little nuances that I need to point out. When you're doing these synthesis reactions, you can choose that I only want the para product here. I don't want the ortho product. It would be ortho and para. But when you're doing synthesis, you can just write the product that you want as long as this reaction gets you that product. Okay, so in this case, I just want the para product, so that's the one I'm going to write. Am I going to make some ortho product? Yes. So in real life, we'd have to figure out how to make this, how to do this reaction and limit the amount of ortho product, because the ortho product is going to cut down on our yield. And ultimately, we want to cut down on the amount of waste. And if we're in an industrial setting, waste is cost. So we want to make this molecule as inexpensively as possible, because otherwise we go out of business, unless we have huge government funding, but that's for another class, not organic chemistry. So we want to try and make this as efficiently as we can, but in this case, we could just pick the para product. So now I could go ahead and now I could oxidize with KMNO4, because now I've got my groups in the right position, and so now I could oxidize, and then that would give me as my final product the CO2H, the carboxylic acid, along with the SO3H. So sometimes when we put a group on the ring, we will just put that group on, then add the second group, because that group is directing where we need the other group to go, and then we will transform that group into the final group. So we have to think about the sequencing of these reactions depending upon what the ultimate substitution pattern is. So I hope that makes sense. If I oxidize the alkyl group, I would end up with this product over here. So I've got to put the alkyl group on, then put the SO3H group, then convert the alkyl group to a carboxylic acid. Okay. So these are the kinds of things we think about, but I can't stress enough the fact that you need to know your transformations. And there's a summary sheet that is a resource on the Canvas website, but you really need to know all of those transformations. That can help you, but you really need to know all of your transformations in order to figure out how to sequence these reactions to get the product that you want. Basically, these sequence of reactions can be thought of as words or letters, and if you use an incorrect transformation, it invalidates the synthesis. Now, I'm going to be a little more forgiving and not necessarily take all of the points off, but if you want to get maximum points, you're going to need to make sure that you have all of your reactions and that they work. They give the product you intend them to give. Okay, so this is sort of a newer example of how can we add a CO2H group on the ring. So now what we're going to need to do is we're going to need to learn how to put some of our groups on the ring that we have as directors. So for instance, do I know how to put an alkyl group on the ring? Check. Do I know how to put a halogen? Yes. Do I know how to put a carbonyl? Yes. Do I know how to put a nitro group? Yes. Do I know how to put an OR group? No. Do I know how to put an NR group? No. Do I know how to put a benzene ring on Yeah, I could just use Friedel Crafts for that. So how do I put a C triple bond N group? Don't know. So we have to learn the reactions on putting those groups now on the ring. So let's start with the idea of putting an NH2 group on the ring. NH2 is placed on the ring in a series of steps where we reduce a nitro group. So remember, reduction means, in this case, add hydrogen or loss of oxygen. In this case, I'm going to lose the oxygen and add hydrogens on a nitro group. I know how to put a nitro group on the ring. Again, just as review, how do we put a nitro group on the ring? We react the benzene with nitric acid and sulfuric acid, and that will put the nitro group on the ring. Now, to reduce that, we use either tin or iron, HCl, and heat. This combination of reagents then reduces the NO2 group to an NH2 group and forms the amine. And this molecule is called an aniline, is its IUPAC or common name for this NH2 when it's attached to the ring. It's an aniline. So we can put an NH2 group on the ring by putting a nitro group and then reducing it with iron, tin, HCl, and heat. Okay. So that's how we can do that. Now, once we form that, we're going to see that we can do a lot with an aniline. We've already talked about how to put benzoic acid on the ring through either a Grignard or through oxidizing an alkyl group. So we've already talked about that. But the idea of putting an NH2 group on the ring leads us to a series of reactions that will allow us to put an OH or a CN, C triple bond N group on the ring. And this is to basically prepare what are called diazonium salts. Now, a diazonium salt, we take our NH2, our amine, and we react it with HCl and sodium nitrite. Okay, so this is NO2 is nitrite as opposed to NO3, which is nitrate. So when you react an amine with HCl and sodium nitrite, you end up forming this RN triple bond N. This nitrogen has a positive charge, and there always has to be a counter ion, which in this case is the chloride. So what we have is we have this diazonium salt, and it's called a diazonium salt because it's an N plus Cl minus. Now, we've just made a molecule with a nitrogen gas molecule embedded within it. Alkyl diazonium salts are not stable, and they tend to be explosive. You know, if one of the fun facts you've taken out of this class is if you want to make something explode, embed a gas molecule in it, take that as a fun fact, not something that you should actually do, unless you work for companies that do that, like the Nobel Company, or I don't know, any other company, legitimate company, that does that. But this, with an alkyl group, there's no stabilization there. On the other hand, if we take our aniline that we just made and we react it with HCl and sodium nitrite, we can make an aryl, sort of a phenyl, an aromatic diazonium salt, and that's stabilized because of the conjugation between the N triple bond and the ring. And there would also be a Cl minus as the counterion here. So you don't have to worry about blowing anything up if you use a benzene ring with an NH2 to make the aryl diazonium salt. So one of the things we can do then is we can prepare aryl diazonium salts by starting with an NO2 group, which we showed how to add the NO2 group. Then we reduce the NO2 group with iron or tin and HCl and heat to form the aniline with the NH2, and then we react that with HCl, sodium nitrite, to form the diazonium salt. Once we have the diazonium salt, we can do lots of things with it, including what are called the Sandmeyer reactions. And so the Sandmeyer reactions are when you take a copper 1, this is a copper +1 salt, of either copper chloride, copper bromide, or the critical one, copper cyanide, and you react it with this diazonium salt, you end up putting that group on the ring. Well, you could say, but chlorine and bromine we already know about, but C triple bond N is new. So this is the way we could add the C triple bond N, the nitrile group, onto the benzene ring, is through this Sandmeyer reaction. So it's going to take a it's going to take a nitrobenzene to aniline to diazonium to C triple bond N to put a C triple bond N group on the ring. Once you have that diazonium salt, then you can do lots of things with it. You can react it with H3O plus and put an OH group on the ring, which is great. You can react the you could take that diazonium salt and react it with HBF4 and put a fluorine on the ring. There's lots of drugs, things, I think Prozac is one of the drugs that has fluorine on the benzene ring. Lots of ways, lots of important molecules have fluorine on benzene ring. This is the way you can put it on there, through the diazonium salt. You could put an iodine on the ring using potassium iodide or sodium iodide with the diazonium. And you can actually take the diazonium salt and replace it with a hydrogen with H3PO2. Might be a reason to do that in the future, but all of these are important reactions because now they let us put the OH group on the ring, a fluorine and iodine. And so now I think we've actually completed our chart in terms of putting all of these groups on the ring. We know how to put a C triple bond N on there now. We know how to put a nitrogen group on the ring. We'll talk in a later lecture video on how to put the alkyl groups on the ring. We know how to put an OH group on the ring, and the OH group is going to be our lead into putting an OR group on the ring, and I'll actually add that reaction. I'll talk about that in a moment. So these diazonium salts give us the ways to put those other groups on the ring. There are other aromatic reactions that we can use, and an important one is forming a Diazo dye. And so a Diazo dye is a compound that has a benzene ring attached to an N double bond N with another benzene ring, and typically it has an activating group on the other side. This is a basic structure of a dye that you can use to dye fabrics. And there's a whole story, which I won't go into at the moment, of William Henry Perkin, who was basically, he was like a middle to high school student in England. He had a chemistry lab in his basement, which means his parents were fairly well off, and he was trying to make a cure for malaria, which is called quinine, and he was using different mixtures, and he ended up with something that was really dark in color, and as he kept diluting it, he actually found out it was purple, and he basically developed the royal purple color that at the time was like all the rage of fashion in Paris. But normally the purple color came from taking these insects that you got off some island in the Mediterranean and crushing them up, which is why there was a limited amount of purple dye and why purple was associated with royalty. Well, William Henry Perkin was able to make a dye that was purple that then was accessible, and that led to basically the modern chemical industry. People found out that they could then make drugs, and he was doing this through coal, using compounds that came from coal tar, and I'll talk a little bit more about that in future episodes. So what you can do is, if you take this diazonium salt, it does have a resonance structure where the N plus can be on the end, and when you react that, this is now my E plus, and it will go to the para position if you have an activated ring, and so basically I just add that to the benzene ring. So what these diazonium, Diazo dyes, we see them in general chemistry lab, or we see them in analytical as acid-base indicators. So here's methyl red, which is a Diazo dye. And it's red in acidic conditions, it's yellow in basic conditions. So it's an acid-base indicator that you could use in a titration, or you could use to determine is your solution acidic or basic. And there's lots of these Diazo dyes that do that. They have different colors. There's orange and deep yellow and yellow red and deep red in terms of forming those kinds of compounds. So Diazo dyes are important in terms of being able to form these different acid-base indicators, but they also are dyes, and historically they led to the idea that we can take organic molecules and we can synthesize medicines, we can synthesize dyes, we can synthesize industrial materials from those. And I guess the one thing I haven't said is that you get aromatic compounds. The mother's milk of aromatic compounds is coal. And so that's in part the reason why organic chemistry developed in Germany, because of a lot of the coal reserves that they have. And that's actually what fueled their chemical industry all the way through both of the world wars. So I want to go back and just kind of finish up looking at these groups that we now have learned how to add to the benzene ring. And we do know how to add, for instance, the OH group here on the benzene ring using the diazonium salt. But how would we convert that group into an OR group? And let's just go over that, because we actually know how to do that. So if I was to say, okay, I would like to convert benzene into an OCH2CH3 group, an ethoxy group. I can't add the ethoxy group directly, but I can certainly add an OH group to the ring and then convert that OH group into an ethoxy. And if you're kind of thinking, well, wait, how would you do that? The way that we would do that is simply by converting in this case, the phenol, which is what this is, into the corresponding alkoxide, or what is called a phenoxide, and then reacting the phenoxide with a CH3CH2Cl group, so that it would basically do an SN2 reaction to give me then the ethoxy group, to convert basically the phenol into an ethoxy. So this is just nothing more than a Williamson ether synthesis, and this is of course an SN2 reaction. So then the question is, how do I deprotonate my phenol and form a phenoxide? And there's lots of reagents that we can use for that. We could use a C-, we could use an H-, we could use NH2-. We could also use sodium, we could also use potassium metal, right? We're just reviewing now all the ways to make the alkoxide in a Williamson ether synthesis. But since this is a phenol, remember a phenol is more acidic than a regular alcohol, so we could also use hydroxide, because hydroxide will completely deprotonate a phenol to make the phenoxide as well. So that means we would just need to basically put the phenol group on the ring. How would we do that? We would use HNO3, H2SO4 to put the nitro group on the ring. We would use iron or tin, HCl, and heat to reduce that to an NH2 group. We would then use NaNO2 and HCl to make the diazonium salt, and then we would use H3O plus in order to convert that ring, or convert that diazonium to the phenol. So what you're gonna realize very quickly is that if you want to add an OH group, or if you want to add a nitrogen and NH2 group, is what we'll use for the moment, or if you wanted to add a C triple bond N group to the ring, that you're going to have to put the nitro, reduce it to NH2, and then make the diazonium salt to put the C triple bond N or the OH group on the ring. So it's going to be required, you know, at least 4 steps in order to be able to do that. And we'll talk about the synthesizing different molecules, some strategies, in not the next lecture video, because the next lecture video will talk about some organometallic reagents that can be used to add complex alkyl groups to the ring. But in the next one after that, we'll review some strategies on synthesis. So just so you're aware, we can use all these different reactions that we've learned about in the past to change an OH group on a ring into an OR group to make an ether out of it. Now, my suggestion is that if you want, that this would work great to put a primary or a secondary alkoxide on the ring. If you wanted a tertiary, if you wanted to put a tertiary group, then what I would do is I would just simply use like tertiary butoxide or tertiary butyl chloride and have it react with the phenol, because the carbon-chlorine bond would break. You would end up with the carbocation, and then the phenol would just simply add to that to make the ether in a standard way. So while the Williamson ether synthesis cannot be used with tertiary to make tertiary ethers, it could be, the phenol could be used directly. The only thing you're not going to be able to do is to protonate this OH group and have water leave, because for the most part the putting a carbocation on the benzene ring in terms of putting it on a carbon-carbon double bond is not stable. So you'd have to use your alkyl halide here. You could just say, well, couldn't I do this? Use phenol, tertibutanol, NH plus. Yeah, you could do that too. Just don't. This carbocation will not form. It is too unstable. So anything you do to avoid that would be great. Okay, so that's how we can convert the OH group into an OR group. So now we can put all the different groups on our chart on the ring. So the last topic that I want to kind of discuss is the idea of what's called blocking strategies. So the other thing we have to be aware of is that in a real synthesis, we're trying to maximize our yield. So for instance, let's say that somebody said, you know, I want you to make this orthobromotoluene. Methylbenzene has a common name of toluene. I want you to make that, And if you were working in an industry, you would try and make this in the highest yield possible, because unless you have somebody else who wants to buy the para-toluene or the para-bromotoluene, you'd then have to separate and do all of these steps. Plus, it wouldn't be necessarily environmentally friendly and generate a lot of waste. So could we think about using a strategy to make orthobromotoluene in the highest yield possible? And in order to do that, we need to talk about what's called blocking. And blocking is exactly what it sounds like. Let's put a group on the ring that blocks that position. But in order to do that, I got to be able to take that group off. So this needs to be reversible. The one reaction that we've talked about that is reversible is sulfonation. So it turns out that you can put an SO3H group on the ring using SO3 and H2SO4. You can take it off of the ring and replace it with the hydrogen using steam. And so in this case, we can actually put an SO3 group on the ring to block that position and then take it off using steam. So let me show you how we would accomplish this synthesis using a blocking strategy. So what we might say is, if you were going to do this reaction, you might say, well, okay, how about this? I have to make the methyl group and the bromine. So what I would say is, well, let's go ahead and let's put the bromine on the ring. And then we would just go ahead, and we would do that by using Br2 and FeBr3 or FBr2 and aluminum tribromide. And then if you said, well, why don't we just go ahead and use methyl chloride with aluminum trichloride and do Friedel-Crafts alkylation, the problem is that we would actually alkylate both at the ortho and the para position. So we would make our desired product, but we would also then make the para product. And now we'll take into account steric hindrance, because in this case we would probably get the para product as our major product because of the steric hindrance of adding the methyl group next to the bromine. Now at this point we would write both of these as products, but in reality when we went to the lab we would probably get mostly the para product, which would be fine if that's what I wanted to make. But in this case I want to make the ortho product in the highest possible yield. And you could also take the approach and say, well, why don't you put the methyl group on the ring first? And you could do that. You could try either one of these. There would be advantages and disadvantages to each, but you could say, well, let's put the methyl group on the ring first. You may have been saying, why didn't you do that to begin with? Well, there's two ways to do this. So if I put the methyl group on the ring and then I said, well, let's go ahead and react that with bromine and FeBr3, what's going to happen? Well, the bromine again is going to go to the ortho and the para position. So in this case, I'm going to get some ortho bromotoluene, but I'm probably going to get a majority of the para bromotoluene. And that's probably going to be my major product. So in either case, if I want to make para-bromotoluene, this would be a great method. I'd have to separate a little bit of the ortho product out, but this would make this as the major product. But I want to make the ortho as the major product. So what should I do? Well, here's what I would think about. I would say, okay, I want to put the most activating group on the ring first. So I would put the methyl group on the ring. And then I would say, you know what, I want to block this para position. So what I would do is I would add SO3 with H2SO4. Now the SO3H group is huge, right? And so it would form almost exclusively the para product because of steric hindrance. So I would get then the para SO3H addition as, if not 100% yield, pretty close to it, because of the steric hindrance in putting that group, putting two groups next to each other on the ring like that. So now once I did that, I would say, okay, now let's go ahead and add the BR2 and the FeBr3. So the methyl group, remember, is the highest on the chart, and it's going to direct to the ortho position to itself, because the para position is now blocked by the sulfonic acid. And so that means that the bromine is going to end up ortho. And now, to get to the final product, I just use steam. So I use steam, I strip off the sulfonic acid group, and now I've made my ortho bromotoluene in the highest possible yield. So this blocking strategy can be used when the groups are kind of sterically hindered to kind of force two groups together. The SO3H group would definitely add mostly para, if not exclusively. But then if I want to force the bromine into the ortho position, then I would block the para position, put the bromine in. But again, a blocking strategy requires that you take off the group that you just put on. And just my final point is that if we go back and look at our diazonium salts, you might think of maybe this H3PO2, maybe that's a blocking strategy that you might use to put the diazonium on and then basically take it off again. I don't know a circumstance where you would do that, but it certainly could be done. So there's a lot of things to think about when we're doing synthesis, when we're taking a benzene ring and converting it to the different substituents. The first thing we have to do is know our reactions, but then we've got to think about, how do I put the groups on the ring, and then how do I sequence the reactions to get them in the right positions. And so that's what we'll talk about after the next lecture video. The next lecture video will basically complete all the different reactions that we need to know, and then the video after that will talk about some synthesis and some strategies that we would use in order to do these synthetic type problems, and there are plenty of practice problems on the Canvas website. Okay, so that's the end of this lecture video, and the next one will be organometallic reagents that we can use in order to put different types of alkyl groups on the ring.